So here's another example. Again, let's read the question all the way through. A gold-colored pebble is found in a stream. Its mass is 23.2 milligrams, and its volume is 1.20 cubic millimeters. What is its density in grams per cubic centimeter? Is it gold? Notice there are two questions. And then we're given some information in parentheses. The density of gold is 19.3 grams per cubic centimeter. We read it all the way through. We're going to go back and look at what the numbers are. So we've got 23.2 milligrams, and we've got 1.20 cubic millimeters. And then we've got this number down here of 19.3 grams per cubic centimeter. The question is, what is the density? And the units are specified. So we're trying to find density in grams per cubic centimeter. So we need to make some sort of a path down here, and we're going to end up with grams per cubic centimeter as our final. What are these things that we're given? Well, let's write them out. 23.2 milligrams and 1.20 cubic millimeters. It does identify them. If it doesn't, we could do it from the units, but it says the mass is 23.2 milligrams. So this is the mass. The volume is 1.20 cubic millimeters. The question asks, what's the density? Then we need to search our brains and say, well, what is density? Oh, there's an equation for density, right? Density is mass divided by volume. Well, look, they gave me the mass, they gave me the volume, right? That's great. Let's look ahead a little bit and see that, well, that's not what I meant to do. Down here, what are we trying to find? We're trying to find the density in grams per cubic centimeter. If we just take these guys and take the mass in milligrams and divide by the volume in cubic millimeters, are we going to end up with those units? No, we're not. There's two things we can do. There's two approaches. We can convert the units first and then put them into the equation, or we can find the density and then convert the units. Which way do you want to do it? Convert first? Usually students prefer that. So let's take the mass and the volume, and we're going to get those into the correct units first. So let's look at the mass. For the mass, we have milligrams and we need grams. Those are both metric units, and we have one prefix, so that's a one-step process. So 23.2 milligrams times a conversion factor, and what goes on top is the grams, because our path is milligrams to grams. So on the top line here, milligrams to grams. Then milligrams goes in the bottom so that the milligrams will cancel out, and that's how we change the units. To get the number in there, we go into our brain and we say, what does milli mean? Milli means 10 to the minus third. So I'm going to write 10 to the minus third up here. So let's look at that, because these metric units, This is very important. So I'm going to write over here on the side, and then I'm going to erase it because I'll need the space. So if we have a conversion factor that is gram over gram, that's numerically equal to 1, isn't it? And if I had milligrams over milligrams, that's also equal to 1. All these conversion factors have to be equal to 1. The top has to equal the bottom. We've used things like 1 foot and 12 inches. Well, doing it like this doesn't help us convert the units. But what if instead of writing the M, what if I wrote what it means? Milli stands in for 10 to the minus third. Those are equal. Milli multiplies things by 10 to the minus third. So if we put 10 to the minus third on one side and milli on the other, those would cancel out, the grams would cancel out, this thing is equal to 1. That doesn't work if you put the milli and the 10 to the minus 3 together. Okay? I'm showing you a pattern for using metric prefixes that once you understand the pattern and you follow the pattern, it's going to work every single time. It's not the only way to write these out. Some of you may say, well, I prefer to think of it as being 1,000 milligrams in a gram. Well, that's fine, but don't confuse other people. So what I'm going to teach you is you memorize what the prefixes mean in terms of 10 to the something, and then the 10 to the something goes on one side and the prefix goes on the other side, and it'll always work out. Okay, so that's why we've got 10 to the minus third on the top and the milli on the bottom. So 10 to the minus third, remember that's 1 times 10 to the minus third, so that you can do that on your calculator. So on your calculator this would be 23.2 times 1 EE minus 3 equals, and that's going to be 0.0232 grams. 0.0232 grams. So just as an aside for those of you who like numbers, what we're doing there is we're moving the decimal point 3 places. So these metric conversions, if you understand the powers of 10, you can actually convert metric units without using your calculator. If that makes sense to you, you're not going to need me to show you how to do it. If that doesn't make sense to you, don't do it. Just use your calculator. But there we've converted the mass into grams. Then we need to convert millimeters cubed into centimeters cubed. So we've got millimeters cubed, and we're going to go to centimeters cubed. So I'm going to follow the pattern. We look at this and we see millimeters and centimeters, both of them have prefixes. That means we should do it in 2 steps. And so we're going to go to meters cubed and then to centimeters cubed. There is a much shorter way to do it, but we're not going to do that. We're going to do it the long, hard way. So what do we have here? 1.20 millimeters cubed. This path has 2, only to make that longer. This has 2 arrows, so we're going to have 2 conversion factors there. That's not really the right color gray to make that disappear. Close enough. Pesky copyright symbol. So these are cubed units, units raised to a power. So let's put the conversion factors in there without the cube and deal with that later. So we're going to ignore the 3's for now. We're going to go millimeters to meters to centimeters. Millimeters to meters to centimeters. Millimeters are going to go down here. Meters are going to go down there. What does milli mean? Well, we just did that with the grams. It still means 10 to the minus 3. So up here we have 10 to the minus 3. I'm sorry, this is getting very tiny down there. What does centi mean? 10 to the minus 2. So the 10 to the minus 2 goes on the bottom because centi is on the top. And the 10 to the whatever goes on the other side of the line from the prefix. So that would work great if we were converting millimeters to centimeters. But it's millimeters cubed to centimeters cubed. And so we need to cube this whole thing. We need to cube this whole thing. That means that the numbers inside get cubed. I should probably get out my calculator. So how do you do that on your calculator? Well, most calculators have an x to the 3, an x cubed button. So the best thing to do here, you go 1.2, we're multiplying by the top, times, and it says 10 to the 3 minus 3. Well, that's 1 times 10 to the minus 3. So that's 1 EE minus 3. That is a single number. And then I'm going to cube that with my x cubed button. And then I'm going to divide by 1 EE minus 2 and cube that and press the equal sign. And it's going to tell me 0.0012. And that would be centimeters cubed. Can you get your calculator to do that? So kind of some weird numbers, and we're cubing stuff. And the good news is we're not going to do things like this very often. Yes, question?
Now, do we wait to, we shouldn't get the significant numbers?
That's coming.
Not yet?
No, I'm actually going to do that before I do anything else. I just wanted to address any calculator issues first. Anybody have any calculator issues? You have a question?
Yeah, can you just say what you cubed again?
I cubed this, the 1 times 10 to the minus 3rd, cubed. And then when I went divided, and 1 times 10 to the minus 2, and I cubed that. Some students find it more, it just makes more sense to them to just multiply by this 3 times and divide by that 3 times. And if that makes more sense to you, that's great. That's fine. You'll get the same thing. Especially if your calculator doesn't have an x cubed button, that might work better. Any questions about the calculator math part of this? So what about the significant figures? How many significant figures are in 1.20 cubic millimeters? 3. We have a trailing 0 here. There's a decimal point. Now over here, what my calculator showed me, how many significant figures does that have? 2. What do? We need to add a 0. Your calculator doesn't put this 0 in because your calculator doesn't understand sig figs. But when you just convert a metric unit, you don't change the number of significant figures. And so you need to be aware that, oh, that 0 is still there. Okay? So any questions about those two, converting mass and volume into the units that I need before I plug them into the density equation? Okay, so let's make some space here. We'll do this in a different color because this slide gets kind of cluttered up. So we were trying to find the density. And the density is mass divided by volume. And it doesn't really look like much of a different color, does it? Oh well. So the mass is 0.0232 grams. Always write the units. And the volume is 0.00120 cubic centimeters. So we do that on the calculator. 0.0232 divided by 0.00120, and the calculator gives us 19.3333 repeating. So when I put a bar over the 3, that means repeating. And what are the units? I don't have space here, but the units are grams per cubic centimeter. How many significant figures should the density have? 3. Because the mass had 3 and the volume had 3. So we're going to round that to 19.3 grams per cubic centimeter. And that is my answer for the density. That answers the first question. Don't neglect the second question. Is this pebble gold?
Yes.
Yes. Yes, it is. It looks like gold and it has the same density as gold. There are very few things that are that dense. So then we need a second answer. The second answer is yes. Now, I am not going to get hung up and require that you give all of your answers in complete sentences. Scientists generally aren't hung up on complete sentences. We're more fond of complete phrases, or just flat out answers. I mean, if it's a yes or no question, yes or no is fine. Is it gold? Yes. Why say any more? But you have to write it down, and I have to be able to find it. Okay? Exams, multiple choice, it's not going to be an issue. Lab reports, I need to be able to see where your answer is. Any questions about this one? Yes?
Now, if it was 19.1, would it be still gold?
That's a good question. So what if it came out to be 19.1? How would we answer, is it gold or not? Well, let's look at that. Where is the uncertainty in our calculated density? It's in the last digit. So if there's uncertainty in the last digit, and the difference between that and the actual density is only in the last digit, then that's essentially the same. Because our measurements have error in them. The published density of gold is something that has been done many, many times, and anytime you do a measurement repeatedly, you get rid of a lot of the random errors. It's also been done with much more precise instruments than what were used to measure the volume and the mass of this little pebble. So that's a good question. If it came up, even if it came up like 20 or 18.5, that's still pretty close. If it came up like 12, no. And we won't ask you to make a judgment call on something like that.
So they'll always turn out exactly.
It'll either turn out really close or really far off. If this was just a spray painted pebble, the density would probably come out to be like 2 or something. Gold is incredibly dense. Any other questions about this one? Yes.
Is it possible you can show us how to convert after finding density?
Yeah. Yeah, so let's do it that way. I think what I'll do is I'll just erase everything. Isn't that nice? Ta-da! So let's do this the other way. We'll calculate the density and then we'll convert the units. So density is mass over volume. So we'll take the mass, 23.2 milligrams, and we'll divide it by the density, the volume, 1.20, not centimeters, cubic millimeters. and we're going to end up with a number. It'll be the same number, just with the decimal place in the wrong spot. 23.2 divided by 1.20. So, oh, funny. 19.3, but the units are milligrams per cubic millimeter. That's funny. But the units are wrong. It doesn't always end up that way. Exactly. This is a coincidence. And I'm guessing they did that on purpose to be funny to the teacher. So what do? Well, we'll take this over here, milligrams, I'm going to write it over cubic millimeters. So it's always good to have a path. Whether you need to write the path down or not depends on just how familiar you've gotten with this. So we have 2 units to convert, and so we're going to consider them separately so that we don't get mixed up. So let's start on the top because that's a good place to start. So we'll go milligrams to grams. Then we'll deal with the millimeters. Millimeters cubed. And here I'm going to show you that shortcut I said I wasn't going to do. Millimeters to centimeters. Okay, so if you're at all familiar with a metric ruler, how many millimeters are in a centimeter? 10, right? So this is one that it is fairly easy to figure out. If you were going millimeters to decimeters or something, I'd say don't try to do a shortcut. But millimeters to centimeters, we can do this in one step, but we have to recognize that there are 10 millimeters in 1 centimeter. And that's not something that you easily, quickly get from just looking at prefixes. But from looking at rulers and knowing that there's millimeters and centimeters, that's something that some of us would know. And so we'll use that here. So milligrams, we're going to multiply by something with grams on the top, milligrams on the bottom to take care of the milligrams. Well, let's put the unit in. The numbers in. So milli means 10 to the minus 3. So I put 10 to the minus 3 up here. And if it makes you feel better, put 1 times 10 to the minus 3. That takes care of our first unit conversion. Now we're going to look at the other one, but we can just string it right along in here. So we're going to go in here, and we're trying to get to centimeters. Now we don't want to put the centimeters on top, because the unit that we're converting is in the denominator. So to cancel millimeters cubed, millimeters has to go on the top. We want to end up with centimeters on the bottom. So it's kind of upside down. So we're going to put millimeters on top and centimeters on the bottom. Again, I'm ignoring the cube until I get this all straightened out. I look at what I wrote down over here, and there's 10 millimeters for each centimeter. We can also do this the way we did it previously using the 2 terms. They'll just both be flipped upside down. And this whole thing needs to be cubed. Now the cubic millimeters cancel with the cubic millimeters, and we end up with cubic centimeters. So 10 cubed is 10 to the 3rd power, right? So we end up with 19.3 times 10 to the negative 3 times 10 to the positive 3, which ends up being 19.3. Grams per cubic centimeter. I would put a box around that and then answer the other question, which is yes. I think for most students, just learning how to do dimensional analysis is more straightforward to convert the units first. And even if you go through this and you calculate the density and you realize, oh wait, the units are wrong, it still might be simpler to go back and convert the mass and convert the volume and calculate the density again. Any questions?
So the millimeters are canceling out, not next to it in the second equation of the first one.
Right. So millimeters cubed here cancels the millimeters cubed there. And it's important that we have this 3 cubing the whole thing. Any other questions? So here's another one. These are more interesting word problems, more challenging, or more frustrating, depending on your point of view. A titanium bicycle frame contains the same amount of titanium as a titanium cube measuring 6.8 centimeters on a side. Use the density of titanium to calculate the mass in kilograms of titanium in the frame, and what would be the mass of a similar frame composed of iron. And they gave us a picture, which is always nice. If you're not given a picture, sometimes you should draw a picture. I've gotten pretty good at drawing pictures in my mind, but if you need to draw a picture on the paper, you go right ahead and draw a picture on the paper. We're going to need the density of titanium. It says use the density of titanium. They didn't give it to us. Let's go back. Back here somewhere is a table. So this table has the density of titanium in it. Titanium 4.50, and important to look at the units, grams per cubic centimeter. So before I mess up my slide, I'm going to go over and get this, 4.50. So the density of titanium is 4.50. So density equals 4.50 grams per. Okay, that didn't work out very well. Let's put it over here. Density equals 4.50 grams per cubic centimeter. We're going to need that. So we're looking at a bicycle frame, and we want to know the mass of the titanium in that frame. It's telling us that it has as much titanium in the frame as in a cube that is 6.8 centimeters on a side. Could we figure out the volume of the titanium? Yeah. The volume of a cube is the length times the width times the height, which is all the same. So it's 6.8 times 6.8 times 6.8. So the volume is 6.8 centimeters times 6.8 centimeters times 6.8 centimeters. So the calculator is giving me 314.432, and the unit will be cubic centimeters. How many significant figures should that number have? 2. 6.8 has 2, and so this is going to have 2 significant figures. But that's not our final answer, so I'm just going to make a note of it by underlining that first uncertain digit. This number has 2 significant figures. I'm not going to round it off, though, because that would introduce some error. I'm just going to keep track of it only has 2 sig figs. So we have the density and we figured out the volume. Can we find the mass of this? Yeah. We can use the density as a conversion factor. So we're going to take this volume, 314.432 cubic centimeters, and I'm going to decide that we don't need this picture anymore. I need space more than I need the picture. Isn't that fun? Yeah, I get paid for coloring. Okay. Now we can use that space. So there's our volume, and we want to get mass. So we have our density. But maybe we should actually write out our path here. We kind of started and then we're like, oh, wait a minute. So I'm going to write the path down here, cubic centimeters, and with density we can convert to grams because the density relates grams and cubic centimeters. But what's the question asking for? Kilograms. Can we convert grams to kilograms? Oh yeah, we could do that. So we're actually going to just do those one after the other. From grams we're going to convert to kilograms. So cubic centimeters to grams to kilograms. Cubic centimeters to grams to kilograms. And that's going to give us our answer in kilograms. Then we put the units in so they cancel out. We want cubic centimeters down here. We want grams down there. So these units are all going to cancel each other out. Do you see how I'm doing that? Hopefully it's making more sense by now. Units are in. Now we need to put in numbers. Well, the grams per cubic centimeter comes from the density. 4.50 is with the unit gram. They have to stay together. So the 4.50 goes on the top. Sometimes the number goes on the top, sometimes the number goes on the bottom. The units tell you where to put it. The next term, kilograms to grams. What does kilo mean? 10 to the third. So kilos on top, I'm going to put what it means on the other side. That's 1 times 10 to the third. So I haven't done any calculations on my calculator since I did the volume. That number is still here. I'm not going to type it in again. I'm just going to use it. So I've got that number, 314.432, and I'm going to multiply by 4.5, and I'm going to divide by 1 to the third, 1 times 10 to the third. And my calculator is going to give me 1.414944, and the unit on that is going to be kilograms. Now we need to look at significant figures because calculate the mass in kilograms. That is a final answer. Well, the density has how many sig figs? 3. So there's 3 here. Kilograms to grams is an exact conversion, so we don't have to worry about that. How many significant figures does this number have? Well, as I wrote it, it's got 6, but where did it come from? It's only got 2. So that is going to limit our answer, and so our answer is 1.4 kilograms with 2 significant figures. Any questions? Yes? Doesn't have a decimal after the 1? Well, let me try that again. Well, I get the same thing. Are you dividing by 1 times 10 to the third? Are you using the EE button? Try doing it dividing by 1,000. I'm guessing it's a scientific notation issue with the calculator. No? There's another question. What would the mass be of a similar frame composed of iron? We need the density of iron. Can somebody tell me what the density of iron is? 7.86. Okay, so we'll make this a different color. We'll make this orange. So the density of iron is 7.86. Did I remember that correctly? Okay. So how would we calculate the mass of this frame made out of iron? It's the same calculation, isn't it? We're just going to use a different density. So just because I can, I'm just going to pop that number in here. So 7.86. Do that calculation with 7.86. 314.432 times 7.86 divided by 1 times 10 to the third, 2.47. $143,552 kilograms, which would, again, is going to have two significant figures, so 2.5 kilograms for the iron. You see why they make bicycles out of titanium? The really, really expensive ones? Titanium has a much lower density than iron, and so you can have a metal object of the same size, the same volume, but it's going to weigh a lot less. Any questions? Here's a very expensive lesson in the importance of units. In 1999, NASA lost a $94 million orbiter because there were two groups of engineers working on this, and one was using metric units and one was using English units, and they were not clear with each other, and so the calculations were wrong, and so the orbiter descended too far into the Martian atmosphere and burned up. Oops. Units are important. Here, $94 million, and man hours and embarrassment, you know, in the national, I mean, in the world, it's like, oh man, those dumb Americans and their screwy units. But you know, you're going into the medical field and you screw up on a unit, you could kill someone. You know, if you had grams instead of milligrams or something like that. So, you know, sometimes students feel like we're being too picky about the little details. But there are situations, more than you know, where little details have tremendous outcomes. And they can cause, you know, really bad outcomes. So details are important. And yeah, you know, getting the decimal point in the wrong place. Well, I got the right number, the decimal point's just in the wrong place. Yeah, that doesn't count, okay? It's right or it's wrong. So here's a problem that we could do related to that issue. Suppose the Mars orbiter was to have established orbit at 155 kilometers, and that one group of the engineers specified this distance as meters, 1.55 times 10 to the 5th meters, and the second group of engineers programmed the orbiter to go to 1.55 times 10 to the 5th feet. What's the difference in kilometers between those two altitudes? We can solve this problem. Now this is probably, for those of you who don't like word problems, this is probably one that's, makes you think about the aliens and the pancakes on the roof and the color purple or whatever that was. You're like, oh my goodness. And we can figure this out. So we have one group of engineers. In fact, I'll give you an example of drawing pictures. So here we have these engineers. Oops. We have these engineers over here, these guys. And they're saying that, okay, all of our things are calculated for 1.55 times 10 to the 5th meters. And then you have this other group of engineers over here, the green engineers, and they're saying 1.55 times 10 to the 5th feet, because they're using the English system, because they're stubborn. The question is, what's the difference between those two altitudes in kilometers? So how do we find a difference? We subtract. But can we subtract feet from meters? No, because that's like apples and oranges. You can't have 5 apples and take away 2 oranges. This just doesn't work that way. What we have to do is we need to convert these into the same unit. We have 2 distances here, one in meters, one in feet. We need to convert them so that they're both in the same unit, and then we can subtract them. And it wants the answer in kilometers. So maybe we should just convert them both to kilometers. Not the only way to do it, but let's just do it that way. So then we've got 2 conversion problems here. So meters to kilometers. Well, if we look at the question here, they actually gave us that in kilometers, right? 155 kilometers. They just wrote it out like this. So we don't actually have to convert that one. This is the same as 155 kilometers. So we need to take the feet and convert to kilometers. So feet to kilometers. We're going to start with feet. And we're going to end up with kilometers. How are we going to get there? Does anybody know the relationship between feet and kilometers? I don't.
1
From feet to meters and meters to feet.
1 foot equals what?
0.3048.
0.3048 meters. Did I get that right?
Yeah, that's what my calculation was.
Okay, awesome. So, student looked this up and found the relationship between feet and meters. So we can use that. So that tells us that we can go from feet to meters. That's not something we had in our heads, but we were able to look it up, so that works just fine. And then can we go from meters to kilometers? Yeah, that should be really easy. If I was doing this completely out of my head and not looking up a conversion, I'd have to go feet to inches to centimeters to meters to kilometers. More steps, but we could get there. So 1.55 times 10 to the 5th feet. Our path is feet to meters to kilometers. 2 arrows, 2 conversion factors. Feet to meters to kilometers. The previous unit goes in the bottom, so feet cancel out, and meter comes down here, meters cancel out. Units telling us what to do. We have this relationship. It was 1 foot and 0.3048 meters. Kilometers to meters, we remember that kilo means 10 to the 3rd. Kilo's on the top, so we put 10 to the 3rd on the bottom, which is 1 times 10 to the 3rd. So we've got 1.55 E5 times 0.3048 divided by 1EE3 equals. So that is 4.7244 kilometers. We are looking for the difference between these two. So this guy up here, and how many significant figures would that have? It would have 3, so 4.72. So up here, this one is equal to 4.7244 kilometers. Should have zoomed in to write that. I'm underlining the 2 because that's where the uncertainty lies. What's the difference between 155 and 4.72? Well, we just subtract them, right? 155 minus 4.7244 equals. You got 47? Okay, I did something wrong. Thank you. Okay, 1.55E5. You guys need to speak up sooner. Yes, 47. One of the problems is, the one thing I don't like about the TI-30XA is the decimal point is tiny. And my eyes are getting old and it's hard to see it. So, okay, let's fix these guys. It's like magic. 47.244. Still 3 sig figs, still kilometers. Up here, that is equal to 47.244 kilometers. So we've got 155 kilometers minus 47.244 kilometers. Which is a difference of 107. Where would the uncertainty lie in that number?
Do we round? What away?
Well, this is our final answer. 155 has uncertainty in the ones place, and 47.2 has uncertainty in the tenths place. This is subtraction. So the uncertainty in our answer is going to be in the ones place. The calculator is saying 107.756, and so we would round that to 108. 108 kilometers. That's the difference in orbit altitude. And I think a kilometer is 1.6 miles, isn't it? Yeah, so it's like 172 miles. That's going to cause a problem, like your orbiter crashing and burning in the atmosphere of Mars. Oops. Any questions? My question is, how on earth did they not catch that? It makes a great illustration of the importance of units. So then the chapter 2 in review. So these slides, I'm not going to go over them, but they are available to you on PowerPoint. These just kind of summarize the things we covered in chapter 2. We talked about uncertainty, we talked about units, we talked about density. These are skills, not just concepts, but what should you do using scientific notation, reporting measured quantities, the right number of digits, counting significant digits, rounding, using sig figs in different sorts of operations, converting units and calculating density. End of chapter.